All right, let's do this. To this very full room right now. I hope everybody can hear me. All right. Okay. We're going to kind of pick up with something that we left off with last time. We talked about internal energy, which is the amount of energy that we have in a chemical system. Right? And we said we're not really concerned with the value of U, but rather changes in U. And we said that we can change U one of two ways, using either the Q, which we had defined previously as heat, and then the W, which we talked a little bit more about last class. What was W? Work. So these are two ways that we can transfer energy into our chemical system. And we spent a little time talking about the work portion in particular. We said that work was equal to negative external pressure times change in volume. Okay? And we said how this is very important for certain systems. We highlighted like a car engine, a combustion engine, which is actually powered by work because of that change in volume that occurs in the cylinder. All right, but really any reaction we could carry out at a fixed volume, and many reactions don't even involve gases. So like there's not even a change in volume to worry about. If we think about a precipitation reaction, for example, we mix two solutions together. We have this chemical reaction occurs, but there's no change in volume in that chemical system. All right, so now we're going to focus on chemical systems that are at constant pressure and volume. If the volume of this system is constant, what happens to this equation here? Delta U equals Q plus W. If delta V is 0 because we're at a constant volume here, how can we simplify this? It's just Q, right? That work means if there's no change in volume, then work is 0, so this drops out. All right? And so at constant pressure and volume, the only way to change the internal energy of that system is by adding or removing heat. All right? And under these special conditions, we give this a special variable name here. We don't call it Q anymore. We call it delta H. All right, so at constant pressure and volume, changes to our internal energy are equal to changes in this new variable delta H, which we call enthalpy. Okay? Now, truthfully, enthalpy is a little bit more complicated than this. This is a special case where we can simplify our function for enthalpy. You'll go on and you'll take a thermodynamics class in grad school where they'll give you all the nitty-gritty details about enthalpy. We're kind of focused on this special case here where we have a system that is, again, at constant pressure and volume. Okay? All right, so now we're going to introduce this new term here, enthalpy. And this is going to kind of be a big focus for not only the rest of this class, but also next week as well. Enthalpy, we use this variable delta H. Okay? And so what is our enthalpy here? Our enthalpy is a measure of the thermal energy or heat exchanged by a chemical system. And we're going to add that little caveat at constant pressure and volume. Okay, So to be clear, why do we use Q sometimes and delta H other times? We use delta H specifically to refer to chemical systems. We can talk about adding heat or taking heat away from, say, just like a hunk of metal, all right? And then we would tend to use the variable Q. When we're talking about a chemical reaction or a phase change, we use this variable delta H here, okay? You've actually seen delta H before, if you remember, when we were talking about phase changes. We had our delta H of fusion, delta H of vaporization, and that was just the kilojoules released or absorbed per mole of whatever it is that we were talking about. All right, so when we're talking about a chemical system, we like to use this delta H variable here. Okay, we're going to have some fancy terminology here for when the sign of delta H. So when delta H is less than 0, i.e. is negative. What did we say when Q was negative? Was that a system that released or absorbed heat? Released, and so same thing here. When delta H is negative, this is a chemical system that is releasing thermal energy. Release heat. All right, and we have a fancy term for chemical systems that release heat. We call those exothermic. Okay, a good example would be just like an acid-base reaction. When you mix an acid and base together, if you're holding a test tube once you mix these two together, you will feel that test tube physically warm up because of the release of heat that occurs during that reaction. And when delta H is positive, this is going to be a reaction that doesn't release but rather absorbs heat. And again, we got a fancy term for this. We call these processes endothermic. All right, we're going to use this terminology throughout the day today. Okay, enthalpy is going to be the first of these what are called thermodynamic variables that you're going to be introduced to in your chemistry career. We're going to throw another one at you next semester, which is a little bit weird. It's called entropy. This semester, our focus for thermodynamics is going to be on this particular variable here, delta H, enthalpy. And there's one thing about all of these thermodynamic variables that make them super duper useful. And that is the fact that enthalpy is what we call a state function. This means that its value depends only on the initial and final state of our system not how we got there, right? So basically the bottom line is it doesn't matter if you do a reaction in one step or if you break it up into 1,000 little steps, the change in enthalpy here will be the same. All right, because all that matters is where you start and where you finish, not where you go in the middle. Okay, so that's a little bizarre. All right, we're going to use a physics quantity here to kind of help us wrap our heads around what the heck it means to be a state function. All right, so again, state functions. Okay, we're going to use these physics variable or these physics quantities because they're a little bit easier to wrap our heads around. And what we're going to imagine is that we're going to go to the mountains, and we got this gigantic mountain here. And our goal is to get to the top. All right, and we got two hikers on this mountain, the red hiker and the blue hiker. And both of these hikers are going to start in the exact same place. All right? Our blue hiker is going to take off up this mountain, and it's going to do the nice leisurely switchback route. Back and forth up this mountain until it gets to the very top. Okay? Our red hiker is feeling all sorts of ambitious, and they're just going to beeline it right up the side until they get to the very top here. All right, they took the steep route. So they're both going to start in the same place. They're both going to finish in the same place. So let's think about this. In terms of the distance traveled, which one of our hikers traveled the greatest distance, took the most steps to get up that mountain? The blue hiker, right? Their path is a lot longer. So our blue hiker took the longer path up that mountain. Right? So in terms of steps, steps made to get up there, your blue hiker took a lot more steps. But there's another quantity in physics that's very similar, but not quite the exact same thing, called displacement. All right, and displacement is simply the difference between where you finish minus where you started. And in terms of the displacement of these two hikers, which one is greater? They're the same, right? Trick question. They're the same. They both started in the exact same place. They both ended in the exact same place. So our displacement for our red hiker and our blue hiker are equal. All right? That is because distance is what's called a path function. It depends on the route that you take, right? Or in this case, the physical path you took up the mountain, all right? But displacement is what's called a state function. It doesn't matter how you got there. The only thing that matters is where you start and where you finish, all right? Enthalpy is an example of a state function in chemistry. Doesn't matter how you get from A to B. All that matters is where you started at point A and where you end at point B, okay? But of course now we're not talking about walking ourselves up a mountain, we're talking about a chemical system. So it doesn't matter how many steps this chemical reaction takes, all that matters is where we start and where we finish, okay? So let's just kind of illustrate this as best we can here. Enthalpy as a state function. All right, we're going to take a look at a simple chemical reaction. We're going to take two NO2 molecules, and these will combine to form dinitrogen tetraoxide gas. All right. Now let's say that we do this in the lab and somebody measures the amount of heat that's released or absorbed by this reaction so they can tell us what the delta H of this reaction is, okay? And when they did this reaction, they just converted their nitrogen dioxide into dinitrogen tetraoxide all in just one step, okay? But then somebody else came along and they did another experiment where they took that dinitrogen tetraoxide, they took their nitrogen dioxide, there it is, and they first decomposed it into nitrogen gas and 2 moles of oxygen gas. and they measured the amount of heat that was absorbed or released in this particular reaction. We're going to call that delta H1. And then in a separate step, they took their nitrogen and their oxygen gas, and they made that same product, that dinitrogen dioxide. Dinitrogen tetraoxide, holy cow. And again, measure the delta H of that step. We're going to call that delta H2. So now they took 2 steps to get from A to B here. All right, but importantly, in both of these 2 labs, in both of these 2 experiments, where they started and where they finished were the exact same. All right, so that means that if our second scientist were to take those 2 enthalpy values, delta H1 and delta H2, and add them together, they would have to get that same delta H of that first reaction, right? Because the only thing that matters for enthalpy is where you start and where you finish. Doesn't matter if we break it up into a bunch of different steps. The bottom line is, at the end of the day, the change in thermal energy will be the same. Okay? Cool, fantastic, all right? This turns out to be the most ridiculously useful property of these thermodynamic variables that you could have, all right? We'll try to illustrate how that is here in a second. The first thing that we need to do, though, is we need to kind of develop a new skill, and these are what are called formation reactions. We need to learn how to write some new chemical equations here. All right, so what we're going to do is, given a chemical compound, so for example, we're going to use our favorite go-to sodium chloride here. We're going to write a chemical equation that is the synthesis of our compound. Where we start with each element in their standard state. Okay? So what do I mean by that? We have our compound, sodium chloride. I'm going to write a chemical equation for the synthesis of sodium chloride. All right? So remember, synthesis reactions. That means I got a lot of reactants combining into that one product. And my product is going to be that sodium chloride. So we're going to write a chemical equation here for the synthesis of sodium chloride. And our reactants are going to be all those elements in our compound, but in their standard state. So I need sodium in its standard state and chlorine in its standard state, my 2 elements in that compound. All right? I'm going to be good with my states of matter here. My state of matter of sodium in its standard state is what? Solid. And what about chlorine in its standard state? Gas. And not only that, what else am I going to remember about chlorine in its standard state? It's diatomic. Awesome. So Cl2 gas. All right, so we have this synthesis reaction of sodium chloride starting with each of our elements in their standard state. All right, there's another kind of weird thing about these formation reactions, which is totally illegal in any other balancing that we've been doing thus far. And that is, we're going to balance this chemical equation specifically so that our product side coefficient remains 1. We're going to force that product coefficient to be 1. So then the only way that we can do this is by using fractions to balance our chemical equation. All right? So formation reaction, synthesis of a compound starting with each element in its standard state, and we're going to balance with fraction coefficients so our product coefficient remains 1. All right, so my sodiums are balanced. However, my chlorines here are not. In order to balance those chlorines, I'm going to use that fraction coefficient of 1/2. So I got 1 on the left and 1 on the right. All right, again, this is not legal in the way that we were balancing chemical equations before, but specifically for these formation reactions, we're allowed to do this. Okay, now our coefficient of 1, we don't actually write the 1 just like normal. All right. Importantly, though, on our reactant side, we may see these fraction coefficients for our formation equations. All right? Cool. So, before we move on, I want y'all to practice. You're going to give me the formation equation for magnesium oxide and potassium phosphate. All right, so magnesium oxide, what are my reactants going to be? Magnesium and oxygen. So I'm going to do magnesium in its standard state, which is a solid, and oxygen in its standard state, which is a diatomic gas. And now I need to balance my formation equation. I'm not going to touch the coefficient on the product side. That's going to remain 1. So instead, I'm going to balance with a 1/2 for my oxygen here. Okay. What about our potassium phosphate? What are my reactants going to be? Boom, all of them, right? You're breaking this entire thing up into all of its constituent elements. So we're going to have 3 reactants: potassium, phosphorus, and oxygen, right? All of which in their standard state. So potassium is a solid in its standard state. Phosphorus is also a solid in its standard state. And again, oxygen is that diatomic gas. I'm going to balance this such that my coefficient remains a 1 on the product side. Here I don't have to use my fraction coefficients, right? You don't always have to. Boom. So here's my balanced formation equation for this potassium phosphate. All right, so we're learning about these new types of reactions here, really just chemical equations, these formation equations, where I'm going to give you a compound, and you're going to give me a chemical equation where the reactants are all those elements in their standard state. And then these are balanced in a weird way where the product side always remains 1. So maybe we have to use these maybe we have to use fraction integers in our, not integers, fractions in our balancing. Cool. All right, so we're going to grab this magnesium oxide as an example here. All right, why do we care? Why do we make a big deal about this? All right, so it turns out that we can look up, we got this table here. Let's just take a look. Okay. This is this table of what are called thermodynamic quantities for all these various substances. What the hell is this? Get out of here. I don't know what this box is. Doesn't matter. Let's go down. Okay. Anyways, we got this giant table. So this is just a copy of the appendix from the back of the Tro textbook here. And what we see is a list, an alphabetical list, or it's alphabetical by element, of just a ton of different compounds. Right? All these compounds that we've kind of talked about, maybe some that we haven't, are all listed on this table here. Okay? Again, let's focus. We talked about magnesium oxide, so let's zoom in. Here's our magnesium oxide. All right? And what you can see here are these values that are given for that compound. One of which is this delta H value. Again, that's the focus of the course today, or the class today, enthalpy. Okay? The other two columns, I know everybody's very anxious to get to use. We won't be talking about these until next semester. All right? We're going to focus only on that enthalpy value. We'll talk about G and S next semester, but right now it's all about that delta H. And what you can see is that it's delta, not only is it delta H, but it's got this little, it's got this little F here as well. That's because what's given to us is the delta H of the formation reaction for all of these compounds. So when I look up this value right here for magnesium oxide solid, and I get this negative 601.6 kilojoules per mole, what that tells me is that this formation reaction right here, our formation reaction, has a change in thermal energy, a delta H of negative 601.6 kilojoules per mole. Let me shrink this down. Negative 601.6 kilojoules per mole. Cool. So we got this table of compounds. What is this table telling us? We can look up our compound here, and the value that's given is the delta H of that formation reaction that we just learned how to draw, our chemical equation for. Okay? So for example, we could all, right, we also did sodium chloride. Let's find sodium. Boom. Right? We got this value, negative 411.2. That means that that formation reaction for sodium chloride releases 411.2 kilojoules of energy per mole. All right? Cool. So, step one, we're just going to take this and we're going to talk about enthalpy stoichiometry. Everybody's favorite word. All right. Not going anywhere. Okay. So now I have this chemical equation here, and I looked up that delta H value on the table. And now I want to know if 4.5 moles of magnesium oxide are produced, how much heat is absorbed or released. All right, we're going to do this one together. And then I'll set you free on another example here. Okay? All right, so we're going to need to use our enthalpy value that we just looked up on our table here. Okay? It's written kilojoules per mole. So in order for our to turn it into something that we can use in our math, we're going to make this negative 601.6 kilojoules over 1 mole. All right, our conversion factor here. Okay? So then I'm going to do my math. I'm going to start out with my 4.5 moles of MgO. Okay? But now this is an important sort of subtle thing about these delta H values that are given. They're given as kilojoules per mole. But kilojoules per mole what? All right? Importantly, when we get a delta H of a reaction, we say that it is in units of kilojoules per mole of reaction. So what the heck does that mean? All right? When we draw our balanced chemical equation, we have stated what 1 mole of reaction is. According to this balanced chemical equation, 1 mole of reaction is when 1 mole of magnesium combines with half of a mole of oxygen to produce 1 mole of magnesium oxide, right? So when we do our delta H values, they're in kilojoules per mole, but it's kilojoules per mole of reaction. And when we draw our balanced chemical equation, that's when we say what a mole of reaction is, according to that balanced chemical equation. So if I'm going to be good with my units here, what I'm going to do is I'm going to multiply this by that stoichiometric ratio, which says that 1 mole of magnesium oxide is consumed per mole, produced per mole of reaction. And now my units are in the right place to multiply by that delta H, which is negative 601.6 kilojoules per mole reaction. All right, so punch that into my calculator. I get negative 2707.2. All right, what are my units? Kilojoules, because moles of magnesium cancel out, moles of reaction cancel out, so I'm in units of kilojoules. And then we still got to do sig figs. To be clear, those values that you get from that table are indeed measured values. There's nothing exact about an enthalpy. So when I do my sig figs, I'm going to say, all right, this number has 2, and this number has 4. So I'm going to round this off to 2 sig figs here. So if 4.5 moles of magnesium oxide are produced, that means that I've got negative 2,700 kilojoules of energy. And what could we say? Is that energy released or absorbed by this reaction? Released. All right, and I kind of missed an opportunity here, but looking at that delta H value, what would we say about this reaction? Is it exothermic or endothermic? Exothermic, right? A negative delta H is an exothermic reaction. Cool. All right, then given what we just discussed here, I want you to do one more enthalpy stoichiometry problem for me. Okay. Now let's say if 1.36 moles of O2 is consumed, how much heat is absorbed or released? All right, so I'm going to start out with my 1.36 moles of O2. But before I can use that enthalpy, I need my units to be moles of reaction, right? So I'm going to use my balanced chemical equation. According to my balanced chemical equation, how many moles of oxygen are consumed per mole reaction? 1/2. All right, so I have 1/2 moles of O2 per mole reaction. And now I'm in the correct units to multiply by that enthalpy, negative 601.6 kilojoules per mole reaction. Importantly, when you punch this into your calculator, you're dividing by this fraction, so to keep your order of operations, you need to put that in parentheses. All right, so if you got a different value than I get here, make sure that you're thinking about your order of operations in your calculator here. All right, we should get negative 1636.352. And our units here are moles of oxygen cancel out, moles of reaction cancel out. So we're in kilojoules. And then how many sig figs? 3. Okay, so if 1.36 moles of oxygen are consumed, that means that this reaction is going to release 1,640 kilojoules of energy. Cool? All right, so we got this table. Big scary table with a bunch of numbers on here, bunch of compounds. Again, we're only going to pay attention to that first column. The other two we'll get to next semester. All right, and that first column tells us the enthalpy of those formation reactions. All right, our units are kilojoules per mole. But when we go to do our stoichiometry, we're going to remember that it's kilojoules per mole of chemical reaction. And the mole of reaction is stated by your balanced chemical equation. However you balanced your chemical equation and found delta H, that's a mole of reaction. All right. Cool, so we're going to kind of roll up these things that we did, but we got one more skill that we need to do here. All right, and that is what we're just going to call math with enthalpy. Let's stick with this same chemical equation that we've been talking about, our magnesium oxide. Okay? So this is our reaction here. All right, now I'm going to take this reaction and I'm going to double it. Meaning I'm going to take this entire chemical equation here and I'm going to multiply everything, all of those coefficients, by 2. Very similar to what we were doing when we were talking about balancing our reactions by half reaction and we had to multiply to get our electrons canceled out. Same idea here. If I take this entire chemical equation and multiply it by 2, that's going to double all of my coefficients. So now it's 2 magnesiums and 1 oxygen gas, because a half times 2 is 1. Gives me 2 magnesium oxides. So what do we think is going to happen to the delta H of this reaction if we double our entire chemical equation? We're going to double it. All right, so if we double our reaction, we're also going to double our delta H. I'm going to take that delta H value of my original reaction and I'm going to multiply it by 2. So now we have a new delta H of this reaction, which is what? 1203.2. Should probably use a calculator. Cool. Okay, so if we were to take a chemical equation and double it, all we're going to do then for our enthalpy value is double that as well. All right, now what if we flip this reaction? Meaning that now I'm not going to say it's magnesium and oxygen combining to make magnesium oxide. But now I'm going to do this decomposition reaction. I'm going to take formerly my product magnesium oxide, put it on the reactant side, and say that this is going to be converted into magnesium and oxygen gas. All right, the exact reverse reaction of what we just had at the top there. Okay? Well, if forming magnesium oxide releases a bunch of heat, then if instead I decompose magnesium oxide, that's going to absorb a bunch of heat. And how much heat is it going to absorb? That exact same 601.6. I'm just going to take this and I'm going to flip the sign of that delta H. So if I flip my reaction, I'm going to flip the sign of delta H. So this reaction here would have a delta H of positive 601.6 kilojoules per mole. Cool? So if we have a chemical equation and we multiply it by some constant value, here I just chose 2, it could be 3, 4, 5, doesn't matter. We're going to do the exact same thing to our value of delta H, and now we have the enthalpy of our new reaction as written. If we were to take this chemical equation and flip it so that now formerly my products are on the reactant side, and I move my reactants to the product side, I flip my reaction, I'm going to flip the sign of that delta H, but the value doesn't change. Cool? All right, wonderful. Now we're going to take all of these little skills that we just built here, and we're going to combine them together to show why these formation enthalpies over here are so super duper useful, okay? At first, if you think about it, it kind of seems like it's not all that great. Like, okay, I got this value for magnesium oxide, but it's a very specific reaction of magnesium oxide. What if I want to take magnesium oxide and do another reaction with it, okay? Turns out that this value is still super duper useful here. Okay, cool. So, we're going to now build our delta H for a reaction. Okay? So, what we're going to do is we're going to take that same kind of sample reaction we looked at the beginning, just because it's kind of simple. We only got one reactant and one product. We're going to take that nitrogen dioxide and convert it into dinitrogen tetraoxide. Okay? And our goal here is to figure out what the delta H of this reaction is. Now, unfortunately, it's not just as simple as looking it up on a table somewhere. There's no table for every reaction that you could think of out there. All right? So instead, what we're going to do is we're going to imagine that instead, we're going to break this up into our two formation reactions. So I want you all to take a second and give me the formation reaction for that nitrogen dioxide and the formation reaction for that dinitrogen tetraoxide. So remember, this is where we take our compound as the product of a synthesis reaction, and our reactants are each one of those elements, in this case nitrogen and oxygen, but they got to be in their standard state. Nitrogen in its standard state is N2 gas, oxygen is O2 gas. All right, remember the weird thing about these formation equations is when we balance, we're going to balance with fractions on our reactant side. We want to keep this a 1 on our product side. So I'm going to need to put a 1/2 out here for my nitrogen. I'm going to do the same thing for the product, the dinitrogen tetraoxide. Again, all of the elements in my compound on my reactant side in their standard state. So again, that's N2 gas and O2 gas. And I want to balance this in such a way that keeps that product coefficient 1. Well, in this case, it would be the same as our normal balancing, but whatever. Balance that with the 2 out front of that oxygen. Okay? All right. So now what we're going to do is we're going to take these formation equations and we're going to look them up on our constants page. We got to get the delta H of each of these reactions. We'll call it delta H1 and delta H2 for our first and second formation reaction. All right, so we're going to go to our constants page. We got to look it up by element in alphabetical order here. So here we got nitrogen. Okay, everybody take a second and copy down the value that we need for that, for where you see one of our reactants here. We'll have to do a little bit more scrolling to get the other one, or one of our compounds here. Right, you need an exact match. Okay, we know about nitrate, but that's not in our chemical equation at all. Right? It's not NO, it's not nitrogen monoxide, it's this nitrogen dioxide gas. All right? Not only that, and this wasn't a great example, but you see here, we have N2H4 liquid, N2H4 gas, right? Not only are you matching your compound formula, but your state of matter as well. You're looking for an exact match on this table. All right, and again, the only value that we're going to pay attention to is that first column, that 33.2. So for that first reaction, H1, what did I just say, 33.2? Yes, 33.2 kilojoules per mole. If I'm just looking at this reaction here, is it endothermic or exothermic? Positive is endothermic. Cool. All right, we got one more compound to look up here. I'm going to look up my product, and again, we need an exact match. N2O4 gaseous state. On my table, I got to do a little bit more scrolling. Now it's all the way at the top over here. All right, we got two N2O4s. Which value am I going to use? That 9.16, because I need the exact match. I want to match that gaseous state there. So 9.16 kilojoules per mole. Endothermic or exothermic? Also endothermic. Also a positive delta H value. All right, now we're going to take these two formation equations and we're going to combine them together to make what we're going to call our overall equation here, the one that we started out. Remember, we started out with this here, and we want to find the delta H of that reaction. And what we did was we broke up all of our reactants and products into these formation reactions. Now we're going to combine these formation reactions together in order to get back to that overall chemical equation here. All right. So our goal, let's just state here, we're going to combine our formation equations. To get that overall chemical equation that we started with. All right, so first of all, what do I mean by combine? This is very much so exactly what we did when we were balancing under acidic conditions or basic conditions, and we split stuff up, and then at the end we added everything back together, right? That's our goal, is to add these two formation equations up in such a way that they will give us our overall chemical equation. All right, but if we just added them up as is, that wouldn't work out so well. All right, so first of all, let's look carefully at this first formation equation. In this first formation equation, our product is the nitrogen dioxide, but in our overall, I'm just going to label this, in our overall equation, that compound is on the reactant side. So what am I going to have to do to that formation equation? What did we learn that we could do last time when we were talking about math of enthalpy? We can always flip our reaction. All right, so that's exactly what we're going to do. We're going to take our formation equation 1 and we're going to flip it. So now that nitrogen dioxide is on the reactant side, and that 1/2 nitrogen gas and oxygen gas are on the product side. And if I flip my chemical equation here, what's going to happen to that enthalpy of 33.2? It's going to become negative 33.2. Okay? Cool, so now I have that nitrogen dioxide on the reactant side, but let's pay attention to our coefficient here. If I want to add these all up to get my overall reaction, well, in my overall reaction, I got a coefficient of 2. So what should I do to this formation chemical equation here? I'm going to multiply the whole thing by 2, right? You can't just pick and choose. You got to take the whole thing and multiply it by 2. So not only are we going to flip, we're also going to multiply by 2. And again, I mean the whole thing gets multiplied by 2. So now I have 2 NO2s. One half times 2 is just 1, so 1 nitrogen gas. And now I have 2 oxygen gases. And what's going to happen to the delta H of this reaction when I do that? I'm going to double it. So now I got negative 66.4 kilojoules per mole. Okay? Let's look at our formation equation 2. N2O4 on the product side, N2O4 on the product side. Am I going to have to flip it? No, I'm good there. My coefficient's 1, my coefficient's 1. Am I going to have to multiply by anything? No, cool. So I'm just going to take this and copy paste exactly as it is. All right, and just like how we learned how to do in that pain in the butt balancing of redox reactions, I want you to take these two chemical equations and sum them up, add them together. Combine all your reactants on one side of a new chemical equation, all your products on another side, and then cancel everything that appears on both sides. So when I sum it up, I put my two NO2s on my reactant side, along with my other reactants, nitrogen and two oxygens, combined onto one reactant side of a new chemical equation. Then I'm going to do the same thing, combine my products onto the product side of this new chemical equation. And then I'm going to simplify here. What can I get rid of when I simplify? I get rid of my oxygens. What else? My nitrogens. And so what am I left with? That overall equation that we wanted. Our two NO2s and that N2O4. And since I summed these up in order to get my overall equation, how can we get the delta H of this reaction here? We're going to sum up those delta H's of those two steps there. All right, so I'm going to take my negative 66.4. I'm going to add the 9.16, and I'm going to line it up at the decimal to be good with sig figs here to show that my overall reaction has an enthalpy of negative 57.24. With that sig fig, we're just going to keep it marked. Kilojoules per mole. So this reaction right here, our nitrogen dioxide being converted into dinitrogen tetraoxide, is that reaction endothermic or exothermic? Exothermic. All right. So we had this overall equation here. This is what was given. And we said we want to know what the enthalpy is of this equation. So what we did is we took our compounds, our reactant, broke that up into its formation equation, and looked up the delta H of that formation equation. We took our product, broke that up into its formation equation, looked up the delta H of that reaction. And then we took these two formation reactions, we flipped, we multiplied by 2, and combined them together, summed them back up, and that allowed us to get the delta H of the overall reaction. Cool? All right, now that is a very long, drawn-out process for getting a delta H here, all right? The good news is we can distill what we just did into a very simple little formula here for calculating the delta H of our reaction, all right? What we did is the delta H for any reaction. What we did was we took the sum of the delta H of our products. We made sure to multiply them by their stoichiometric coefficients. And we subtracted the sum of the delta H of our reactants, again, multiplied by their stoichiometric coefficients. All right? So this equation here is what we're going to use to calculate the delta H for any reaction. What's up?
Sub P stands for products?
Yep. All right, and what I want you all to chant to yourself, anytime you're about to be calculating a delta H here, is products minus reactants. All right, products minus reactants. Just to remember the order of things here, it's always products minus reactants. That's how we're going to get our delta H values. Okay? All right, so then let's do the same thing, but we're going to take the easy route here. All right, we'll take our same chemical equation. We have the same goal of calculating our delta H value. But now instead of breaking it up and flipping stuff around and all that jazz, what we're going to do is we're going to look up our enthalpy of formations for each of these compounds. All right, for the NO2, that was that 33.2. So I'm just going to note right here, 33.2 kilojoules per mole. For the N2O4, that was that 9.16 kilojoules per mole. And now we're going to use our formula here, our products minus reactants. And again, we're going to remember to multiply by our stoichiometric coefficients. So my delta H of my reaction here, I'm going to take my product delta H, that 9.16 kilojoules per mole. Products minus reactants. All right? Now, we only have one reactant. So if you didn't do this time, you'd be able to get away with it. But let me just caution you. In order to make sure that this minus sign hits all of your reactants, you need to put that in parentheses. All right? If you had more than one reactant and you didn't put it in parentheses, you'd mess up your order of operations. You wouldn't distribute that minus sign like it should be distributed. All right? So now I'm going to do my delta H of my reactants, but I'm going to multiply by that stoichiometric coefficient of 2 times that 33.2. Punch that into my calculator, and we better get that same value, or I messed up. Wonderful. All right, so my delta H of my reaction here is this negative 57.24 kilojoules per mole. Per mole what? Per mole reaction. And per mole reaction as written according to my balanced chemical equation right here, right? So according to my balanced chemical equation, 1 mole of reaction consumes 2 moles of my NO2 and produces 1 of that N2O4. Okay? All right, so we're going to do one more. We're going to do it the easy way here. I'm going to give you another chemical equation. we're going to take what's called hydrogen peroxide. This will decompose into water and oxygen. And we're going to calculate the delta H of this reaction. And of course we could do it the long way, but we're going to use our equation for this one. All right, so for each of my reactants and products, I need to look them up on that table. All right, I'll give you a second to finish copying down this chemical equation, and then we're going to bring up our constants page. All right. Don't need that guy anymore. LMNO, we need oxygen compounds. LMNOP, here we go. Cool. So actually all three values that you need are right here in this section. So everybody take a second and record all the relevant values. Again, remember, we're only ever going to be focused on the first column in this course. These are our delta H of formations. We got two waters. Which one should I grab? The gas, because that's what was given to me in my balanced chemical equation. We got two hydrogen peroxides. Which one should I grab? Also the gas, because that's what was given in our balanced chemical equation. And then the O2 gas, notice that has a delta H of formation of 0. What's up with that? All right. Well, real quick, before we move on, let's just think about it. What is the formation equation for oxygen gas? I'm going to put O2 gas on the product side. And then I'm going to write all my elements in their standard state. So what's my reactant going to be? O2 gas. So yeah, absolutely, there's no exchange of heat here. No reaction has occurred, right? So in fact, all elements in their standard state will have a delta H of formation of 0. Cool. All right, so I'm just going to kind of annotate this up top here. We said that the hydrogen peroxide was negative 136.3, and the water vapor was negative 241.8, and oxygen was 0. Remember, we're going to chant to ourselves, products minus reactants. So I'm going to take the sum of my products. All right, that'd be 0 for oxygen. And then I'm going to do 2 times that negative 241. Negative 241.8. and I'm going to subtract the sum of my reactants. I only got that one reactant, but again, I'm going to remember to multiply it by its stoichiometric coefficient. All right. Remember, we got to be good with our sig figs here because this is a addition problem. All right, so when I do products minus reactants, I get negative 211. But again, because my sig figs, it's 211.0 kilojoules per mole. Is this reaction endothermic or exothermic? Exothermic. All right, and remember that's kilojoules per mole reaction. So in my mole reaction, how many moles of water are created? According to my balanced chemical equation, remember when you balance your chemical equation, that's what locks in what 1 mole of reaction is. So 1 mole of reaction would produce 2 moles of water, right? It would consume 2 moles of hydrogen peroxide and produce only 1 mole of oxygen gas. Okay? Cool. All right. We're going to kind of pick up with this next time, but I know everybody's mind is just like blown. This was the most exciting frickin' lecture in the world because what we just learned here is that using this table, as long as you can look up your reactants and products on this table, you can calculate the enthalpy change, how much heat is released or absorbed for any chemical reaction out there using these formation values here, right? So again, the table looks kind of specific at first. It's talking about one specific reaction, but we can combine those reactions together to get the change in enthalpy of any reaction out there. As long as we can look up our reactants and products on this table here, we can say how much heat is going to be absorbed or released by that reaction. Cool. All right. Again, we'll pick up with that next time.